Yeah, Rastafari. DJ Wonder, the original sound. By the talk of the town, sound boy come like a dog of a owner, come like a dog without bone. You get.
Welcome to my talk, how we brought a large C++ AI codebase to C# and Unity. I am Fabio Andrek. I am the team lead for Unity and tools at Kythera AI. So obviously, Kythera AI is the C++ codebase we brought to Unity. So what is Kythera AI? Kythera AI is a game AI middleware for many different C++ engines. One of the features we have is nav meshes, with quite a few extensions. One of them is, for example, autocover, which allows you to generate cover locations from nav mesh data, so your designers don't have to go in and manually add those annotations. Another big feature is 3D navigation. So you can make your spaceships or your airplanes or your submarines fly around in space. And the third big feature is our behavior systems. We have behavior trees, state machines, and utility systems. Right now, we support two big engines. It's the Unreal Engine and Open3D Engine. We also supported Lumberyard and CryEngine in the past. But there is one big engine missing that is publicly available, and it is, of course, Unity. So what's the main difference between Unity and the other engines I have just mentioned? So there are obviously many differences, but the biggest one is the programming language that is used in Unity compared to the other ones. Unity uses C# as the programming language for programmers to use to build games. So our code base is C++, so what do we do? Should we just rewrite Kythera AI in C#? Just throw away 10 years of knowledge, tons of features, well-tested, ported to many platforms, and rewrite the thing in C# just for Unity? Probably not. So the next best thing is building a wrapper for C#. Let's look at the Kythera architecture so we understand how that wrapper could fit in. In general, we have the Kythera core. That's the engine-independent core that does all the magic and implements all our features. So we get data from your game, from the level geometry, for example, and give that over to the core, and the core does all kinds of processing on it. For example, it generates a nav mesh or an octree from that data. Again, this is engine independent. We implement a feature for a specific engine. It will be available on a different engine relatively easy with little integration work. Speaking of integration work, every engine we support, we need an engine integration layer. The main purpose for that is, on one thing, getting data in and out of Kythera, for example, geometry from your level, or then after the pathfinding and avoidance and all that stuff has run, get the data back into your game and actually move the character around. Also, most engine integrations have some kinds of components, so you can define where you want to generate nav mesh and also upgrade your entities to make them agents so they can be controlled by Kythera behavior trees. If we look what we have to change in the architecture to support a C#-based engine, is we still have the core. We still want all those features. And if we build a new feature on Unity, we will also implement that in C++. And so it's available on all other engines too. On top of the core, we have a few C# integration helpers implemented in C++. As you will see later in this talk, there are quite a few things that are not that well supported when trying to bind C++ to C#. C++ has a ton of features, some of them very complex, and they don't really map nicely to C#. So we had to build a few integration helpers, some simple and not so simple functions in C++ to help to bridge that gap. On top of that, we have the C# wrapper that actually makes all the Kythera core APIs available to C#-based engines. And then again, we have the engine integration, which should be basically the same as in other C++-based engines. So again, components, bringing data back and forth between the engine and the game, and the Kythera core. So how does interacting with native code work in .NET and Unity? The technology for that is called Platform Invoke, or Pinvoke for short. It's a well-supported standard .NET technology, has been around since before even 1.0 of the .NET framework. It's well-supported on all Unity platforms, in, both Mono and EL2 CPP platform backends, and yeah, all platforms, consoles, mobile, no problem. It allows calling native code from managed code, that's its main purpose, but also the other way around, calling managed code from native code. So calling C# from C++. This needs quite a bit of magic. I will show you more how it exactly works in a moment. Pinvoke also provides a few low-level APIs, for example, memory allocation. By default, .NET is all garbage collected, or mostly garbage collected. But in some cases, you want to allocate memory directly on the heap, and so Pinvoke exposes a few APIs that does exactly that. There are also marshalling APIs. For example, if you have native structs or even unions, those don't really map nicely to C#, or you have specific memory structures you want to support from C#, so there are helpers for that. And also string marshalling, say if you have a const char star string, and you want to access that as a normal string, you have to make sure it's null terminated and it has the right encoding. So yeah, you get correct conversion between, say, UTF-8 and UTF-16. Here is a quick example of Pinvoke code. This is a very simple example. We have a DLL called Kythera underline core, which has an entry point, a single function called create core, and we make this function available to C# by using this DLL import attribute, and the important thing here is the extern keyword. This is all you have to do. The .NET framework or Unity, depending on which platform you are, will do the DLL loading, look up symbols, and hooks everything up, so you can call this function, or this method rather, like every other static method in C#. We are talking about DLL import. The attribute is called DLL import. The reason for that is just .NET has been built for Windows first, but supports all kinds of platforms now. So you can use the same code, exactly the same code on all platforms. So Linux, no problem. It will just use a .so file instead of a DLL. Let's look at the Kythera core public API that is exposed. We have 90 enumerations, 27 API interfaces. Some of those classes has 50 or more methods. We have 62 aspects. An aspect is basically a component in our internal entity component system, and we have 190 other structs and classes. What I want to tell you with that is we really don't want to write our wrapper by hand. It would be a massive amount of work, and every time we update this API, we would have to update the wrapper too. And again, we have quite a big team. Some of them are working on Unreal, some of them are working on other engines, and we don't want to force those people, if they build a new API, to also work on Unity integration and update that manually. So we're looking for an automatic process. When looking for solutions for that, we found CppSharp. CppSharp is an open source project under the MIT license. It's a subproject of the Mono open source .NET implementation. It is, compared to other solutions like SWIG, specifically built for C# and .NET, which means the code it generates feels really like C# code should feel. Like this has the correct naming convention for variables and methods and classes. And yeah, it just feels like this is code that is actually written for .NET, and it's not just a weird wrapper. It handles some complex edge cases very well, as you will see shortly. And also it's using an LLVM/Clang-based parser, which means you can throw C++23 code at it without problems. Also interesting, obviously, Clang is written in C++ and CppSharp is written in C#. So you can guess what technology they use to actually access the Clang parser. So they are generating bindings to Clang, so they can then generate bindings for you. So dogfooding, like we all should be doing. Let's look at the build process. How can we integrate CppSharp into our build process? Normally, our Kythera core is built by the Unreal build tool or the WAF for CryEngine or whatever build tool is used in an engine. So we don't have to care all that much about platform support. In general, the engine will handle that problem. In this case, we build the integration ourselves, so we have to figure out how we can change CMake to actually work for us on all platforms. And that's not that much of a problem on desktop platforms like Linux, Mac, Windows. It kind of works on Android and iOS too. Console will be interesting to figure out, but we will figure it out. The build process, we are using the standalone CMake build process of our core to get out header files and DLL files. The header files contain our public API, and the DLL files, again, this is, when I say DLL files, I mean platform-specific dynamic linked libraries. So then CppSharp comes in. CppSharp is a library written in C#. So to use that, we have built a C# console project that uses that library. CppSharp will parse the header files and the DLL files to look up symbols in the DLL files, and just to check, does the symbol match to the header files, and can those symbols be looked up correctly? So CppSharp parses the header files, builds an abstract syntax tree from those header files, and then runs a bunch of transformers or translation or passes, basically similar to a compiler passes on the abstract syntax tree to go from the C++ header file structure to actual C# code. And the output of that is the C# bindings. This is basically one massive C#.cs file. In our case, it's 90,000 lines long. Another output is a symbols DLL file. So why do we need that? The symbols library is a CPP file, so generated C++ code generated by CppSharp. And CppSharp automatically compiles that to a DLL. C++ has header-only classes and structs. And for that, no code is generated. It's in a header file only. CppSharp still wants to support those classes and structs. So it generates code in this symbols.cpp file to make that work. One note here is it makes constructors, destructors, and virtual methods available this way. It does not do that for non-virtual methods. So if you have non-virtual methods in your header-only classes and structs, that won't work. You have to move that over into implementation files. Also in that symbols library is a bunch of helper functions to make abstract classes defined in C++ instantiatable from C#. So you can define an interface in C++ and make it then implementable from C#. But for that, we still need to allocate the memory part for the C++ part and also run the constructor for that. And if you want to instantiate an abstract class, that obviously doesn't work. So CppSharp generates code, so you can do that by implementing, like have a default implementation for all undefined virtual methods. Also, class template instantiations are in there. It's a similar thing as header-only classes. It's just class templates only live in headers, so we need to generate a bit of code so we can actually use that. More details on that later. So finally, we are done with our build process. We have the DLL files from core, we have the separate symbols DLL file, and we have the C# bindings. At this point in time, all those files are still engine independent. They work with every C#/.NET based engine. Bindings customizations. In general, CppSharp does a very good job at generating bindings that are nice to use. But maybe you still want to adjust a few things, and CppSharp provides quite a few methods to do that. One of them is C++ macros. So you can add stuff or add macros inside your header files to modify the process on how CppSharp generates the bindings. One of them is csignore file, where you want to ignore the complete header file. Another is csignore if you want to ignore a specific declaration, say a function that you don't need in your C# bindings, so you can just ignore it. Another one is csinternal if you want to, in general, basically CppSharp generates all the classes and structs and functions and makes them available as public from your bindings. So like the userland code can always look up and use everything from your bindings. But if you have helper methods that you still want to have bindings for, but those should be only usable internally, you can use this macro. And there's also CS read-only, which allows you to annotate members of, for example, for a struct, where you only want to get a getter for your property and not get and setter. So if you want read-only semantics. Going over to the customization available in C#. So as I said, CppSharp is a library, and it mostly works by you implementing an interface. The interface provides a few callback methods, for example, preprocess. This is run after the abstract syntax tree has been built by CppSharp. And then, so no processing has happened yet, but the code is all in memory. Then you can run different things on the AST. Basically, you can do whatever you want. But for example, you can ignore a specific class. Maybe you have some very weird C++ code that CppSharp can't cope yet with, and you can get rid of it right here. Another hook is postprocess. This is run after the AST has been parsed and all the translation passes has run on the AST. So right now, we already have the code for the bindings in memory, but we can still modify it. One example we are doing is we have support for both left-hand side and right-hand side vectors in our codebase. And based on a define, we type def to the canonical way we are used, depending on the engine. Because type defs aren't really a thing in C#, we are just renaming the whatever class we want as the canonical one to the real name. So we renamed the kitvec3 LHS to kitvec3. Because we are still in memory, this will update all the references, and there is not much more necessary to make this work. There are a few other places where you can customize it. One is type maps. Type maps is how many internal things in CppSharp are implemented. For example, how const char star is mapped to a string, or integers, how they are mapped to the corresponding C# process. So this is a really low-level way to do mapping. So if you have something very specific and you want some very specific bindings for it, you can use type maps for that. And you can also implement custom passes, which is basically a visitor pattern on the abstract syntax tree, and then you can modify the abstract syntax tree however you want. And the last one is extending classes. So this isn't directly related to CppSharp, but there is a concept of partial classes in C#. This allows you to define a class in two different files, and then the two implementations will be merged together by the compiler. This is very useful in our case. We have a bunch of bindings auto-generated in a file, and we really don't want to modify that file because we want to regenerate it as soon as something changes. So we can create a separate file and then define a separate partial class with the same name and then add methods to that. As an example, again, this is our internal vector, 3D vector class, and we add a method to it that returns a Unity native vector. We also make sure like we get the coordinate system right and all that. So let's look at how or the code that CppSharp generates actually works. The first is enumerations, which is very simple, mapped from C++ on the left to C# on the right. It doesn't matter if your enumeration is scoped or not, it will be mapped to standard C# enumerations. Let's look at a simple struct. We have a simple struct with one member called val, which is this integer, but there is the CS value type macro on top. So this is another CppSharp macro. Why do we need that? There is the discussion about value versus reference types, and C++ and C# handle those quite a bit differently. In C++, if a variable or a parameter is a value or a reference is dependent on the usage. You can use it directly as a value or as a reference or a pointer. In C#, it's different. It depends on how the data structure itself is defined. A C# struct is always a value type. You can't change that. It's always a value type. Same is true for classes. It's always a reference type. So CppSharp in general maps everything, so both structs and classes, to C# classes. So you always get a reference type. If you want to have an actual struct, a value type, you again need this macro. So we want a C# struct from our C++ struct. So how does that code look like? First, we have, as we would expect, we have a struct with the correct name, and we have an internal struct inside that contains our value. This is done because CppSharp also supports things like specific struct layouts or also unions, and so we need those internal struct defined as a separate struct. The data for that struct lives inside the instance member, and that one, as you can see, it's a direct struct or a direct member inside the struct, which means the C++ memory is directly part of the struct. So it's not a separate allocation. If you allocate this my struct in C#, the C++ memory block will be part of that in comparison to the class, as you will see in a moment. We also get a property accessor to the val we have defined. As you can see, it's uppercase, it's the C# naming convention. It's actually generated as a property and not just a public member function, a member value as in C++. Let's look at two additional methods that are generated by CppSharp to enable a few of its advanced features. One of that is create instance. Create instance is used, for example, if we call code, C++ calls C# code. So we get, for example, if my struct is given as a value or a reference or as a pointer, we want to convert that C++ memory block into an actual my struct in C# land. And this is what this method is for. The int_ptr native parameter we get in is basically the this pointer in C++. And then we need to go from that this pointer to an actual instance in C# land. So what we do is we get this void star native pointer, the this pointer, and cast that to our internal struct representation. It's an ugly cast, but casts are very cheap, and we have correctly defined the memory layout, so this is safe. Because this is a struct, this will be a copy. Now let's look at the class. A class is quite similar. We still have this internal struct with our val, but this time the instance is actually a pointer, a reference, no longer directly part of the memory of the class. This is the constructor for that class. As you can see, we are now allocating the instance, so the C++ part of the class, on the heap using alloc h global, which basically is malloc. Next, we have a private member that defines that this class has been allocated on C#. So the C# world owns this instance, which means later on we can release that memory again. In theory, if you have, again, a function or a method that is called from C++ to C#, we might get a reference, and then we should not release that memory because memory is owned by C++. And then we also have record native to managed map. We have this native to managed map, which gave us quite a few headaches. So why do we need that? The native to managed map is a hash map, a thread-safe hash map that maps from the C++ this pointer to the instance of the C# class. You will see why we need that shortly. Take a quick look at that code. What do you expect? We are in a garbage collected language. So we are allocating a list. We add 1,000 instances of our mapped class to it. And then, yeah, the loop is done. And we are in a garbage collected language. So every memory will be released again. It will be garbage collected sooner or later. And we will not have memory leaks, at least in theory. One thing to note is how CppSharp is implemented right now is it cannot or it does not release memory automatically. You have to call dispose method on every instance of classes you have created. Because we have this flag we've seen before, owns memory, it can decide You can always call this both, and depending on that flag, it then actually can decide, can I actually release that memory or not? There is a new experimental feature in CppSharp to generate finalizers. Finalizers are kind of like C# destructors. They are run when a class is garbage collected, and so we can then release the memory if we own that memory, and at the end of when the object is released. We are using finalizers now. There are still a few issues to solve there. Depending on how you do the memory management in a specific class, you might have problems. One thing we are struggling with right now is we have a class that does reference counting, and mapping that correctly to finalizers is quite hard. I haven't figured it out yet, but I'm close. Yeah, just memory management is hard. And also performance. So as you've seen, when we allocate a new class with new, we add it to this native to managed map. So it's a hash map, it's thread safe, so not something we consider fast. It's fine most of the time, but if we do that thousands of times per frame, it will be an issue. And it also allocates heap memory, and depending on how big your class is, this might also be a big overhead. So what are the solutions to get around this problem? One of them is mapping them as a value type. So make sure your class, in our example, we have a color class, which just contains one integer, RGB and alpha, and that we don't really need a class for that. We don't want to allocate that on the heap. So we can just add this CS value type macro again, and we get no dynamic memory allocation. The object will not be garbage collected, and there is no native to manage map. The second solution is get rid of that native to manage map. As you will see shortly, the main use case for this native to manage map is, again, if you want to call code from C++ into C#. And this is mostly done by implementing an interface defined in C++ in C#. So if your class is, say, a vector or a timestamp or a color, which you don't really intend to be inheritable, you can disable this native to managed map code. This feature is currently still work in progress by the CppSharp developers, but it seems like it's already working quite well. So I've been talking about that for quite some time now. Now, finally, I'm going to explain how it actually works and why we want that. This is an example of one of the debug draw output of one of our test levels. This is very exaggerated. I activated everything I could find. We have nav mesh here. We have automatically generated cover rails. We have our spatial query system, debug draw. This is these vertical cylinders. And what we do, the Kythera core defines an interface that every engine integration has to implement. So the Kythera core can tell the engine, hey, I'd like to draw nav mesh. I'd like to draw cylinders. And so we really want to be able to implement that interface in C#. So let's look at a simple example. We have a class that has one public method or one virtual public method called makeNoise. And we have a function noisemaker that takes a class or a subclass and then calls that function. And this is the C# side. This is how the code, after the machinery from CppSharp has run, this is how you can use the code. It looks very natural. If you don't look at the code that is in Animal, you will not really see that this is you're actually overriding or implementing a C++ class. It looks like C#. This is the code that makes that possible. It's horrible. I will not show it to you, but I will describe to you how it works. For every virtual method we have in a class, CppSharp generates a native unmanaged delegate, which is a fancy word for a function pointer. This delegate will be set to an internal hook function that is generated per method. And then we generate a virtual method table in memory. Whenever CppSharp starts up, or the runtime part of CppSharp starts up, it will generate that V table for every class. And then we get a pointer to this native delegate and set that in the V table. Here we can see a struct layout for a class that has a vtable. It's again an int ptr and then that vtable. So this is the hook, the function that is set into the vtable. So if we call we have this interface, we give an instance of that to the C++ side, and then we call a method on the C++ side. This will be the first function that is called on the C# side. The parameter we have in this method is instance, which again is the this pointer to the C++ part of a class. And now we just have this pointer, but we actually need the C# instance so we can actually call our method on it. So then this native to manage map comes in again. We use the get instance method to actually look up the C# instance of our class. Again, it's a mapping from this pointers to the actual instance in C#. After we have done that lookup, we can actually call the make noise function here at the bottom. This is a profiling output from the Unity profiler. I don't know if you can see it well. This is just the get instance call for our debug draw interface. It takes 5 milliseconds, and this is once per frame. So this is clearly too slow. This is obviously full debug version of our DLL and everything, so it won't be that bad, but still we need to optimize a bit here. So one solution is we only have one instance of that debug draw interface ever instantiated. We only need one. So we don't actually need that lookup. We can just hard code one instance, the one we create at startup, and just always use that one. And otherwise, you can't really do much. This is just how CppSharp works. If you have specific use cases and you have to work around that, you need to do something yourself and just build it by hand. C++ templates, another interesting feature that you have generics in C#, but it's really not the same thing. Let's look at class templates first. There is experimental support in CppSharp for those, and you can see the code below. Again, it looks very native. It looks like C#. It looks like you would expect the code to look like. One thing you need to know is it only works for template parameters seen by CppSharp. So it will not guess what your users might be using. So if it sees you use my template with int in your C++ code base, it will make sure you can use int2 in your C# code base. If you try to instantiate my template with float as a template parameter instead of int, you will get a nice runtime exception. Sadly, it's a runtime exception and not a compile time exception, but there is already quite a bit of magic going on to make this work. There are other templates from the standard library, containers and smart pointers. And basically, I have to tell you, not well supported. I would even say not really supported at all, without you having to write a few wrappers around it. For us, thankfully, we already have wrappers around containers because, for example, in Unreal, you have T-vector. They are not directly using STL containers, so they have their own classes anyway, and we have built wrappers for us, so we can actually use containers defined by the engine in our core. And yeah, the other alternative is, as in the good old days, use raw pointers and references. Function and method templates. It's coming soon. CppSharp devs are working on it basically right now. One use case for that, we have a Blackboard implementation. A Blackboard is basically a hash map, but the value is not specific to one type. So you can have integer, floats. I think we also support vectors, our position class, also colors, and a few other things. It's limited, but it's quite dynamic, and it's a standard data structure used in game AI to go between, say, the engine, the game, and our core, and that all uses templated functions. So you have a set and the get method, and they don't really work yet. We have a bunch of wrappers to make that work. And yeah, coming soon, this should be automatic based on whatever is used in our code base. And you can define which ones you want to. So that is supported soon. In the future, we want to expose all the Kythera AI features to C#. In general, at least at the beginning, if we activated a new feature, there might have been problems in CppSharp. Maybe CppSharp itself crashed, or the code that was generated wasn't working, so we gradually add new features. The last few features we have added worked more or less directly out of the box, so that shouldn't be a massive problem. Another thing I want to do is focus on performance. I've talked quite a bit about value versus reference types. So I want to figure out basically for every class, is it worth it to have it as a reference type, or should you have a value type? Obviously, you always have trade-offs, so I want to do some micro benchmarks on that to figure out which makes sense for which use case. A similar thing is method call overhead. How expensive is it actually to call methods from C++ to C#, and also the other way around? Should we do things in a different way? Should we reduce method calls as much as possible, or is that less of a problem? I haven't done detailed benchmarks on that yet. And also memory allocations. Should we do memory allocations as much as possible on the C++ side or on C#, or doesn't it really matter? I just want to do more benchmarks on that. In conclusion, we have a working C# integration. The automated solution paid off very, very well. We realized CppSharp enables a ton of features we didn't really think of when we are searching for an automated solution. Templates, all the property generation, the virtual table code. There's a reason I haven't shown it to you. It's really horrible. And just doing that by hand every time for our 62 interface classes, no, that's great that we have an automated solution for that. And yeah, we had great collaboration with the CppSharp devs, and still do. We contracted them to help us to solve quite a few of our edge cases. We have some special, very high performance C++ code, and yeah, they helped us to make that work. If you want to do something similar, they are always open to work with you. So yeah, there are a bunch of great guys. So I said to you that it's actually now working. So to show you that this is actually true, here I have a clip from Dead House Sonata. Dead House Sonata is an upcoming game by Apocalypse Studios. Apocalypse Studios has been funded by Denis Dyack. You might not know that name, but you have probably heard of Eternal Darkness, Legacy of Kain, or Too Human. So this is his new studio, and building a game on Unity and also using our AI system. So what you're seeing here is, this is a nav mesh. We have agents running around, chasing the player, having a bit of intelligence on how to chase him, and they avoid each other. They do pathfinding to the player, and the control of which abilities do they use, where should they go, is also run by Kythera behavior trees. And no, not yet. It's a very bloody game. And that's it. Okay, that was it from my side. Any questions? I think we should have a microphone somewhere. Yes. Okay. There's a question.
Sorry, were you considering any different systems or solutions than CppSharp?
I've looked at SWIG. The main thing there is they support like basically every scripting language under the sun, and they are not specific to C#. So the code that is spit out by that just doesn't feel C#y, and as I call it. So yeah, that's the main decision why we don't use that. And yeah, CppSharp, it's actually built for C#. And yeah, developers were responsive and were open to help us fix a few issues we found. So yeah, that was an easy decision to go with that.
Very much.
How long did the whole thing take? And did you find it was kind of more or less technical risk than you expected? Full disclosure, I'm Fabio's boss. But,
I think I wrote the first prototype over a weekend in November last year and basically worked on it kind of full time since then. So yeah, it took quite some time, but we built both the C# integration and the Unity integration in those. How many months are that? 6, 7 months. Technical risk, we just had to do it. So yeah, we just did go with it. Yeah, the alternative really is use a different generator, and I think it really is the best one we have found. And the other alternative is doing it by hand. And for that, I guess what we have had to do is build like a C wrapper first, and then write a wrapper for that by hand. And that would have enabled us to produce bindings for other languages. We could do a Python binding, or I don't know, JavaScript. But for now, our focus is clearly C#. So I guess, yeah, we did the right choice. Okay, thank you very much for listening. Follow us on social media. And yeah, go to our website, look at the jobs section if you want to work on stuff like that, or also on Unreal or other engines or on some AI features. Please contact us. Thank you very much.